guys. So today I'm going to give you a short presentation on Windows Media Architecture. This is going to be a fairly high-level presentation that focuses on things like the media pipeline concepts, the components that are inside of each of the media pipeline. That I'll cover both MF components and DirectShow components, also known as DShow components, as well as how the components connect to each other in a pipeline, what data passes through them, how it flows through the components, and give a short description of how to debug MF applications. So to begin with, let's talk about media pipelines. Media pipelines are essentially applications or components in applications that are concerned with processing media data. In this diagram that's going to pop up in a second, I'm going to describe a media pipeline that processes audio data. In this, for example, an MP3 file and plays it through the speaker. So the data comes through from the hard drive in the pipeline, and somehow it gets to the speaker. To the audio card, and from the audio card to the speaker. So this media pipeline will actually process the data, decrypt it, or if it needs to be decrypted, uncompress it and present it in a format that the audio card can understand. So in a media pipeline, all data flows through individual components. In DirectShow, they're called filters. In Media Foundation, they have other names. And these components have independent and different responsibilities. So the data flows, these components are in DirectShow loaded into a graph, and in a Media Foundation application, they're loaded into a similar concept that's known as a topology. So the data flows, in this case, from left to right, from the hard drive to the source filter, which is a component that actually receives the data, loads it from the hard drive, and unwraps the information, if it's in some sort of wrapper in the file, to the transform filter that, in this case, since this is audio, that uncompresses the data. And then finally to the renderer filter that is responsible for presentation of the data to the audio card, and the audio card will, of course, in turn send it to the speaker. So the data flows through the pipeline in individual packets, in individual components, and essentially the same process happens every single time for audio, for video, and for many other media types. For example, if you have a TV stream which has audio, video, for example, closed captioning, subtitles, ITV data, interactive TV data, all of them flow through the same sort of scenario. So here is a slightly more complex pipeline that shows how video data is processed through the pipeline, through the components in the pipeline. So in this case, we have video, once again, data flowing from left to right. Video data is loaded into the file source filter. File source is a common source filter or source component. Source is the name in Media Foundation. It flows into the file source filter, which in turn unwraps the data and splits out audio and video streams. So the data is stored as several streams in the file. The file source unwraps it, unpackages it from whatever format it is stored in the video file, and splits it out and sends it to two subsequent components, in this case the audio decoder and the video decoder, which of course decode the data and present it in the specific format, in whatever format it is the renderer expects it, in this case the video renderer and the audio renderer, which of course in turn present the data to the screen and the audio card. So as you can see here, each of these components has a different responsibility. The file source unwraps the data, the decoders decode the data, and the renderers render the data. There are other components and other component types but these are the main ones. For example, you can have special transformative components that actually add an extra image to the video stream so that you have some overlay on the video, or there are some audio components that modify the data and give you some sort of echo effect, and there are many others. So each of the components is designed to operate on a separate data type. The audio components obviously operate on the audio, but there are different types of audio streams. The MP3 decoder obviously decodes MP3 data, so it's designed to operate on MP3 information. There's MPEG-2 data, and the MPEG-2 decoder is designed to operate and decode the MPEG-2 data. And obviously, since the two encodings are completely different, and since the two data types are different, they cannot be interchanged even though they're both decoders, because you can't really decode MP3 information with an MPEG-2 decoder. And as you can see, if you are familiar with math concepts or with the components in the graph or in a topology are arranged as in a directed acyclic graph. That means basically that the components can never be formed into a cycle, and that data always flows from one direction to the other. So some components in a pipeline can produce data, like the file source in here. As far as the topology is concerned, in this scenario, the file source just produces the data. It could just as well generate the data on the fly programmatically. The other components consume data on one end and do some sort of transformation to it and produce it on the other end, like the decoders here. And finally, there are sync components, or components that consume data and, as far as the topology knows, do nothing to them, or because they have no output inside the topology. These components in this case are the renderers, and they send the data to external devices in this scenario, or they could just throw away the data, or they could write the data to the hard drive. In this case, of course, they represent the drivers for the devices on the machine. So in a pipeline, components cannot be just stuck together willy-nilly. They have to be connected in a specific sequence, that they can understand. So the idea here is that each component must produce data that the component next in line or next in the chain can consume and process. In this case, I'm using the analogy of dominoes, because in a domino game, you have to have each subsequent domino has to have the same number of dots on the input, if you call it that, as on the output of the preceding domino. So this sequence of dominoes is an analogy for a small and basic Media Foundation pipeline, where we have the source that produces data that's in the, let's say, 2-dot format, and we have the transform that consumes data in 2-dot format, does some sort of transformation and change, and produces it in 4-dot format, and another transform that consumes the 4-dot format and produces the 6-dot format, and finally a sync that consumes the data in the 6-dot format. So in this way, both in DirectShow and in Media Foundation, the components hook up to each other in a specific sequence. The dots themselves represent a media type, or what's known as a media type, because what happens inside the components is that the media data is transformed from one type to another. For example, if we have MPEG-2 transform, it receives compressed MPEG-2 data and decodes it, and presumably outputs it in some sort of other uncompressed media format. And each of those formats have media types. Or basically, a media type is a description or a signature for a specific format. And there are hundreds of different formats, and some components can consume data in only one format. Other components can consume data in multiple formats and output data in multiple formats. What exactly the formats they accept is defined specifically by the components, because different components behave differently and have designed differently and so on. So here, let's discuss now the DirectShow graph building scenario. So in DirectShow graph building, we need to basically connect a source filter and a render filter. If possible, we want to make the system automatically discover and figure out which components need to go into the graph in order to play the information or to play a file, for example. So we can, of course, manually say, okay, this is the source filter, this is the transform, this is the render filter, this guy connects to this guy connects to that guy, and so on. But obviously, that's not always feasible, especially in very complex scenarios where you have an unknown file format or unknown file type that you cannot predict when you're designing, for example, a media player. So here is a short animation that shows how automatically the system can intelligently connect and discover the components that go into the pipeline. So what happens is that the system goes through every single transform or every single filter on the machine and tries to discover the filter that fits and works in this scenario. So what happens is it tries every single filter and sees if the media types match for input and output. It tries to tell the filters and output. Tries to tell the filters themselves to connect to each other and see if they're happy with their connection, see if they're happy with the data type. So unfortunately in this animation there doesn't look like there are colors, but basically what happens here let me rewind it and start it again. Basically what happens here is that the system loads first the transform filter 1, sees if because the source filter outputs something that the transform filter 1 can accept, and sees if the transform filter 1 can produce an output of type that the render filter can accept. Then it does the same thing with transform filter 2, and then it tries combinations of filters. So it tries transform filter 3 and 4 and sees if transform filter 4 can produce data in a format that the render filter expects and wishes to consume. In this case, it found the result after several steps, and the same sort of procedure happens on every machine. Obviously, it's not very efficient, but on the other hand, it's much simpler than doing things manually. So in most DShow applications, this is what happens, because in most DShow applications, you don't know what is going to be playing in the application, you don't know what kind of data is going to come in, or you don't know what kind of data will have to come out. So the DShow applications mix and match these different components together to try to build a graph and to try to build a pipeline sequence that will satisfy everybody in the pipeline. So this is a representation of the same procedure that happens in an MF topology. An MF topology is rather more complex than DShow because it has multiple steps. One of the core ideas behind the building an MF topology is that you can pre-build it, you can pre-design it, but not load the components themselves until actual runtime, so that until it's time to actually play the topology and pass the data through, to make sure that you consume as few resources as possible. So what you do is you design the topology, insert the nodes or components, not the actual media components, but objects that represent the components, insert them into the topology, and tell the topology to try to figure out what to do. At runtime, the system, the topology loader, and the session itself load the actual media components that process the data that are represented by these nodes with descriptions of the components, and hook them up together. So here we have, in order to build an MF topology, you need to specify, you cannot just say, okay, here's a file, play it for me. Unfortunately, that's not as simple as that. In an MF topology, what you need to do is you need to say, okay, this is the source of my data, and I want it to play to these specific renderers. I want the data to stream to these specific renderers. And then the MF topology will in turn automatically try to discover the intermediate components. So the procedure for discovering the intermediate components is pretty much the same. It automatically tries to discover the individual nodes that need to be inserted between the source and sink nodes in order to for the data to flow, in order for the data to be transformed properly into the format that the sink expects. And just like with DShow, you can insert other nodes in between the source node and the sink node, and for example, some transformation node. For example, if you want to make the video be black and white, you can insert the black and white filter or transform. Media Foundation transform between the sink and source and sink of the video stream, and tell Media Foundation to try to find combinations of other filters, individual filters or individual transforms or combinations of transforms that will be inserted between these components so that everybody in the pipeline is happy. Each component is essentially a COM object in here in both Media Foundation and DirectShow, and they operate independently of each other. In DirectShow, the components actually know of everybody that's in the pipeline, but in the Media Foundation, the Media Foundation transforms don't know anything about anybody outside the pipeline. So that is very useful in cases where you want to load the components independently of each other, so that or independently even of the pipeline itself, so you can unit test it or use it in other situations or so on. Okay, so since these both DirectShow and Media Foundation pipelines are very componentized, they both provide, both architectures provide or have specific tools that allow you to test it and verify it and find out how things work. So what you can do is you can use in DirectShow, you can use the graph edit tool, where you can, that's the one on the bottom here, the screenshot on the bottom, where you can basically load individual components, individual filters. In DirectShow there are filters, and hook them up manually to each other and say, okay, this is the start filter, this is the beginning, try to hook them up to each other in a sequence and make sure that everything flows. In Media Foundation, you can do the same thing with another tool that does essentially the same thing, that hooks up the individual components to each other, and that allows you to play the components and see their attributes and play around with them outside of your test application. This obviously allows you to test things much more thoroughly and with a lot more outside of the application, outside the complexity of the application, because you can basically put the entire thing under a debugger and see what happens. This is very useful in many obvious scenarios, and even though, and besides everything else, the MF application even allows you to debug it, because the source code for the application is available as a sample in Windows 7 Windows 7 SDK. Okay, so data flows in the pipelines, in both Media Foundation pipeline and the DirectShow pipeline, in separate objects known as media samples. The data, the components are, media samples are basically also COM components, like all the other components in, or all the other objects in both pipelines. The media samples contain chunks of data, chunks of media data that is used that is processed by the individual filters or transforms or sources or sinks. So the media samples contain the payload data, basically a data buffer with whatever is inside the pipeline, whatever media that you are processing, and they contain, besides that, also the attributes, which are sequences or sets of flags that are inserted by various filters or transforms into the pipeline. The flags can contain either, can be just about anything that you want to. They can be, or anything that the preceding components in the pipelines wish to insert. So some of the flags are going to be, some flags can be simply flags, bit flags. Other flags can be structures or sets of data. The only thing that you need to make sure is that the component that's going to be downstream in the media pipeline is going to be able to understand and process that media data. So in DirectShow, as you'll see in a second, because I have some animation there, the media samples are completely reused. So let me go to the next slide. Okay, so DirectShow, here's the DirectShow data flow media pipeline, and the data flows inside of filters between individual filters. And in DirectShow, okay, there's the animation. In DirectShow, the media samples are continuously reused. So what happens is that the graph contains a pool of media samples, and you specify the number of samples at startup. And at design time, or you can do it at runtime, depends on how you design the components. And the samples are continuously passed from one filter to another filter down the pipeline, and when they're released by the renderer, they go back to the beginning. And as you can see right here, they go back to the beginning, and they continuously cycle. So this is obviously very useful from the performance perspective, because this means that you don't have to continuously allocate buffers of data and release data and do that sort of thing. But on the other hand, this can lead to a situation where the graph starves if one of the filters in the pipeline starts hoarding data or stops flowing, passing data through, because there's no more, once there are no more samples in the pipeline, then nobody else can work. This situation is especially interesting in cases where there are multiple streams in the pipeline. For example, if you have audio, video, and subtitle streams, and if the subtitles are for some reason have the wrong timestamps, and therefore they're being hoarded by the playback or subtitle renderer before it's time to actually start playing them or start displaying them, then the subtitle renderer can continuously hoard samples until the entire graph stalls and video stops playing. So in those cases, this is obviously not a very good design, and can be a problem, since even if the user is not playing subtitles, he may not care that they are not being displayed, but he will definitely care if the video and audio are not playing and not working. So to solve that problem, Media Foundation uses a different design where they generate the samples themselves on the fly as they're requested. The samples are basically COM objects, and they also flow through the pipeline. However, in Media Foundation, since the samples are constructed on the fly, what the Media Foundation does is it constructs the sample buffers, or basically the internal data structures which hold the actual media's information, and reuse them. But they, at the same time, while they reuse them, the samples themselves, let me rewind the animation. Let's see. Okay, the samples themselves are created dynamically, but the buffers are used on the fly inside the pipeline itself. So that provides significant performance improvements, because the system doesn't need to continuously allocate new buffers and new data buffers, because the buffers are reused and allocated only when necessary, when the system or when the session decides that more data is required and necessary. So now let's look at the difference, the core difference between Media Foundation and DirectShow. So let me go back to the previous slide. And in this slide, you can see that each filter calls, as the arrows show, each filter calls the next filter directly. So this means that, and this demonstrates that DirectShow systems and DirectShow graphs are essentially a synchronous system. That means that each filter in the DirectShow pipeline knows about the subsequent filter, knows about the filter that's down the pipeline, knows about the graph, has pointers to each of those, and calls the next filter in line directly as a synchronous call. So that makes debugging DirectShow applications very simple or relatively simple, because you can simply walk down the call stack, walk down the call chain, and see which filter is not doing what it's supposed to do, and see exactly what happened before and after this specific call, or what happened before a call that is not working, for example, or where exactly a failure has occurred, because you receive an H result that indicates a failure, and you can walk down the call stack and see what happened. Unfortunately, Media Foundation, due to its design, is more complex. It's an asynchronous system. As you can see in this diagram, the source, MFT, and sync, which are the main component types in Media Foundation, they don't really know anything about any of their surroundings. So what happens is that media session calls into the source and tells it, hey, give me a sample. Media sample, the source returns a sample to the media session. The media session, MF media session, which is a separate component that's part of the Media Foundation framework, the media session takes that sample, does whatever it wants to do with it, and passes it explicitly to the MFT. The MFT has no idea who called it, what component called it, what component passed it data. All it knows is that it has a sample to process. And then media session gets that sample back from the MFT through another call or through an eventing system. We'll go over that in a second. And then the processes that sample, maybe it modifies it, maybe not, and then sends it to a sync, which once again has no idea which component called it. So this allows you, as I mentioned earlier, to process and to use the Media Foundation components outside of the Media Foundation pipeline. You can load them into an external application of some sort. You can load them into a test application. You can load them in a DirectShow wrapper, in a DirectShow graph. The Media Foundation components don't really care because they don't know anything about their surroundings. So at the same time, this makes things a little bit more, or rather more complex to debug and to analyze, because you cannot actually walk the call stack since you don't have the source code for the media session. The media session is an opaque object, and it's very difficult to figure out what exactly is going on in some certain scenarios. So in a second, I'll discuss how to actually try to debug these certain types of applications. Okay, so here's the animation of the media sample. Here, again, the media sample comes out of the source, goes into the media session, then it goes into the Media Foundation transform, the MFT, is processed inside the MFT and goes back into the media session and then passed into the sync. Okay, so Media Foundation transforms come in two types. The transforms are basically the filters that are in the middle of the pipeline. The transforms are filters or components that transform Media Foundation data. Media Foundation transforms come in two types. There are synchronous transforms and there are asynchronous transforms. In synchronous transforms, nothing much happens inside the transform unless the session calls it and tells it, okay, give me data. And so synchronous transforms are pull model because the media session has to explicitly pull data out of the transform. And in some ways, the synchronous transforms are a little bit easier to work with, but they do not account and they don't work very well in scenarios where you have multi-threading available or where you have some advanced functionality that needs to happen. For example, if a transform needs to buffer data and process a bunch of data chunks because it needs to keep ahead of the playback, then it would be a good idea for the transform to be asynchronous, because then it can dynamically say, hey, I need more data, even though nobody is asking it for data, even though the session doesn't ask for it for data. It can keep querying the session for more data, pull more data out of the source, pre-process it, and buffer it for the next time that the sync will request the data. So here in this diagram is a sample of design basically of how a synchronous system can work, or a synchronous media foundation system might work with if you have a custom session. I think I have a sample in the book. I have a sample of this in the book. So this demonstrates basically how the sequence of calls that happens if you have synchronous transforms. So this is demonstrates a very basic audio pipeline where we have basically MP3 data, where we have just a render, an MF transform, another MF transform that resamples things, and the source. So from left to right, from the green oval at the top left, first of all, the source requests data from the session, and the session passes that request on to the first transform in the chain, or the next to last transform, depending on how you look at it. So the session goes up one transform in the pipeline, one transform upstream in the pipeline, and requests a sample from that MFT. The MFT checks that it has no data, and then therefore it needs more data. It needs another sample. It essentially, through the session, calls into the next MFT upstream and pulls that data from that MFT. That MFT in turn detects that it has no data and requests data from the source. The source gets the data. In this case, if we're talking about an MP3 audio file playback, it pulls data, loads data from the file, processes it, stores that data in a new sample, and passes that data. Here we're already going to the bottom blue rectangle in this diagram, passes that data into the next MFT upstream, or actually in this case downstream from it, which pre-processes, in this case, if it's pre-processes the data. If it's an MP3 playback situation, then it uncompresses the data, the media sample, the data in the media sample, turns it into some other format, into basically PCM audio if it's MP3 playback, and passes that new sample, or that sample with uncompressed MP3 or uncompressed audio, to the MFT downstream, which in this case would be a resampler MFT that changes the bitrate of the audio, that does whatever it needs to do and passes it onwards to the sync that still waits for the data for the next chunk of data. That in turn actually plays that information to an audio card or whatever. So the asynchronous model is different in that in a synchronous model, everything is event-driven. Every single action happens because of an event. So when an MFT needs a sample, it fires an event to the session saying, hey, I want a sample, and the session automatically goes upstream. In some ways, it's also a pull model, but this is more dynamic and in some ways a little bit more complex. Because this means that you need to implement, or your MFTs would need to implement several other interfaces and behave slightly differently from synchronous model. So MF supports both synchronous and asynchronous MFTs in the same pipeline, so that shouldn't be a problem. But at design time, you will obviously want to figure out which situation works best for you. Most of the time, synchronous will work for you, except for if you're working with hardware. In that case, you need asynchronous MFTs because that's required, but that's a whole other story. Okay, so now let's talk about debugging media applications. As I just mentioned, the synchronous calls in DirectShow make debugging far simpler because you can simply walk up the call stack or walk down the call stack depending on your perspective and see which filter failed, because every single time that something fails, you'll receive an H result, and for every single call, you'll see a failure. Or you may see a failure, but you'll know exactly when that failure occurred, who failed, when that failed, or at least that's true for most scenarios. There are some scenarios that are synchronous in DirectShows, and they're far more complex, but in most situations, you will not need to deal with that. In almost all situations, it's going to be synchronous behavior. In MF, however, even when you are dealing with synchronous MFTs, the entire design model of MF is asynchronous. Everything is done asynchronously. Virtually every operation that you deal with is asynchronous, and therefore a failure may occur sometime after you make a call. So in this small diagram that you can see here, this diagram shows a sequence of calls that are made by the player and the media session to play back a file. So here the player calls into the media session. Actually, this diagram shows how to close a file, but to close the media session. But the idea is basically the same. The media session calls, the player calls, or basically the player application calls into the media session and passes it a file and says, here's the file, here's the topology played, blah, blah, blah. And after a while, at some point, if the media session fails, it will fire an asynchronous event saying that it failed. But you don't really know when exactly it failed, which call inside the media session failed, which component failed, which operation even failed inside the media session. So that obviously makes debugging and figuring out what exactly went wrong far more difficult and complicated. For that, you have to have various tools, which we'll cover in a second, to figure out what exactly went wrong. Another thing that makes MF debugging far harder, much harder than the DirectShow, is that the MF source code is not available, and therefore you cannot really tell what exactly went wrong since you don't see the source code of the actual components. They are not, the source code is not available to you, so you cannot really step through the media session code and see what went wrong and why it went wrong and how it went wrong. So for those cases, you unfortunately you once again need to use tools that I mention on the next slide. So for MF debugging, first of all, there are two main ways that you can tell what went wrong and how it went wrong. The first method is you can look at the detailed error codes and event types that you get when a failure occurs, because as I mentioned earlier, every single failure in MF is transmitted as an event to you. So you get specific error codes, and the one good thing about MF, or one of the good things about MF, is that it has very detailed error codes that are broken down by specific areas and specific error values that indicate what exactly failed, where it failed, how it failed, so you know where to look and you know how to try to figure out what went wrong. So for example, there's ASF parsing errors, there's media source errors, or specific H-result areas or H-result codes that indicate that, hey, this failure happened in the media source, or this happened during the topology build, or this happened in the renderer. So this will allow you and help you figure out and focus on the components that actually failed and try to look at them specifically in more detail. And the second thing that you can do for debugging of MF application is you can use the MFTrace debugging tool, which is basically a tracing tool that looks into an MF application, an MF pipeline, and tells you what exactly went wrong. So, or tries to tell you. It's a tracing application. I have basically a screenshot of this on this slide. This is a tracing application that's available in the Windows SDK. The application injects itself or attaches itself to a running process, to a running MF process, although it can be attached to any process, and tries to find functions and interfaces that it knows of. For example, it knows all the MF interfaces, it knows the COM interfaces. So it will attach to MF and COM, inject itself into the memory, and detect every single call to that interface, to that specific function. You can configure it to look at individual interfaces, or you can just tell it to trace everything. And it will produce and output various tracing data that will tell you what went wrong and what is going on. So this information can be extremely detailed and very useful. For an example, here's a list of various things that you can see. It's much longer actually in reality than this. And for an example, if you're trying to debug a topology connection issue and start debugging at the very beginning, you'll see the Media Foundation application call functions on every single component in the pipeline. The GUIDs that it passes in, the media types, the media data that the components are trying to process, file names when it's trying to create source components, the internal objects, COM objects that are used by the source creation components to create the right sources, to create the right byte streams, to load the right data, figure out which components it needs to use in the media stream, how the media type negotiation happens, how the samples are passed through, and so on. So this data can be extremely detailed and very useful in many different scenarios because in many situations this is just about the only way that you have to detect things. So what you would need to do, unfortunately, is open this trace log, because you can trace it obviously to the console or you can trace it into a file. Open the trace log, analyze the trace log, look for errors in that log, and search for specific error codes and look up those error codes in the various tables that will tell you what exactly failed and why it failed and why it thinks it failed. And then you can look at the individual components, load them outside of the application or outside of a specific topology even, if you wish to, pass in the data that you expect to fail and debug it in various ways. So this is about it. This next slide basically has a couple of links to MFTrace help documents and MFTrace documentation on the web that you can use that explains in more detail how exactly to debug using MFTrace and what to look for. There are some tools that they provide, or helper tools that they provide that that allow you to find specific error codes or error conditions or parse trace files because the MFTrace files can be very long, like many dozens, hundreds of megabytes, depending on what exactly you're tracing and for how long you're tracing. So these, I highly recommend that you take a look at these websites because they will help you figure out how to use the MFTrace tool properly and simplify your debugging life significantly. So that's about it. So now let me take a look at the questions. Okay, so let me see. Let me look at the log. I think I answered the synchronization question about DirectShow and Media Foundation. The clock is maintained in DirectShow and Media Foundation differently, obviously. In DirectShow, the clock is maintained by the graph. But in the Media Foundation, the clock is maintained by one or several of the renderers. So in Media Foundation, there's actually a clock object that you can create and you can control and specify and pass and give to individual renderers. Most of the time, the clock will be maintained by the audio renderer, but in some situations you may want to give it to this clock and use some other renderer as a control. I believe I have a sample of that and describe that in chapter 8, I think, of the book. Okay, so the next question is, let's see. Interactive TV. So interactive TV is essentially it's an HTML stream that's sent in with TV in various countries, like in Europe, in Japan, in US there's very little of it on main cable. It's an extra stream just like subtitles or audio that contains HTML data or HTML-like XML that is used by the playback application to display various tables or graphics or various other information, and it can be very advanced or very simple. You can pass in and you can do all sorts of things. Display, like for example, during a baseball game in Japan, it's very common to send in an extra table with baseball scores, with extra baseball information. News channels have extra ITV information that shows the weather, that shows some other news information, and for some ITV designs you can even use the ITV, the playback application can even use the ITV data to switch from one stream to another substream in the channel or on the channel to show some other media clip. So it's almost like a computer application that you can use to play back various things. Okay, so guys, if I didn't answer the question, send me a follow-up, and then I'll look through it and try to answer it in more detail. Okay, so the next question is automatic discovery. Okay, so the automatic discovery both in DirectShow and in Media Foundation is done by looking at the individual components in the graph. So, or on the machine. So the components, since they're all COM components, they're registered they're stored in the registry. The information for them is in the registry. There are specific areas in the registry where Media Foundation and DirectShow know where to look for their components. So the information there contained is either can be just the COM name and the COM ID and the file name, or it can be more detailed plus the friendly name like MPEG-2 filter, just a string, or it can be more detailed with, as a hint for the dynamic loader for the topology builder or the DirectShow that tells it what media types this specific component prefers. So if the DirectShow graph or Media Foundation doesn't find the filter that it's happy with or that works with all the information stored in the registry with the preferred media types in the registry, it will just try all the filters in the registry that it can find or all the components in a row exhaustively until it runs out of components to try or until it finds the right combination. So MF doesn't know which components it doesn't need. It has no idea which it needs. It simply looks for combinations of components that will satisfy the source and the sink, or the upstream component and the downstream component. So the upstream component can be an MFT if it's looking between an MFT and a renderer, or it could be two MFTs if you specify two transforms, for example, one for creating black and white video and one for injecting a picture. If they have different requirements, then the MF will look for something to stick between the two MFTs that satisfies the upstream and downstream requirements. Or it could be just a source and a renderer, and it will look for once again for the most basic combination of components that will or the first combination of components that will allow it to pass data between them. Okay, I hope I answered that question. Okay, so which components are software and which components are hardware? So in both DirectShow and Media Foundation, most of the components are going to be software, although Media Foundation has support and provides support for transforms that represent hardware components. For example, the NVIDIA and ATI or AMD now companies provide MFTs that are hardware-backed decoders. So they're decoder components, audio and video, well, video decoders, that are implemented as that show up in the topology as hardware components, but as actually as transforms, but actually represent the underlying hardware of the video card and speed up and significantly simplify the decoding, since they can do it in hardware and do it much faster. In DirectShow, there is no explicit support for that, but of course somebody could write a DirectShow component to do that. It's going to be not necessarily work as well as with Media Foundation, because once again DirectShow is not designed for that, but it's possible. In Media Foundation, the transforms have a specific flag, or you can set a specific flag on a transform that indicate that it's a hardware component, and that represents that it's a hardware object. And during the build, when you're building the topology, you can explicitly say, okay, I don't want to look, or I don't want to enumerate or for hardware components, or you can explicitly start by looking at hardware components and see if there's any hardware component that will do the job that you need, or whatever combination it is. So you can explicitly say that yes, I want a hardware component, or no, I don't want a hardware component in Media Foundation. Okay, so live streaming of a musical band practice with each performing in a different geographic area. Interesting question. To get started in media programming, I would suggest that you start with DirectShow, because that's a much simpler framework. If you've never done a media programming, then that will be that will get you started and get you where you're going faster. Even though DirectShow is right now deprecated by Microsoft, I don't expect DirectShow to go away within the next decade. And however, because it's far more widely used and it's much simpler than Media Foundation. But if you're looking to design something from scratch, then DirectShow will probably be your best bet. Other than that, it depends on what exactly you're trying to do and what kind of architecture you're considering. If you're thinking of, you can design the same system both on Media Foundation and on DirectShow, but I would start frankly by trying to look at existing systems and modifying an existing system to see if you can get things started there, because I suspect that somebody already thought of this. Of course, that's going to be pretty expensive because it's going to be a custom design, but oh well, there's not much else. The alternative is to design something on your own from scratch.